All right. Now for the second part of chapter 13, assignment one. There we go. That's a good way to say it. We're going to talk about the limits of functions of several variables. So first, I want to remind you of how limits are defined in just one variable. So back in Calculus 1, you learned that a limit is essentially what the y coordinate is approaching as the x coordinate gets closer and closer to some number from both sides. So you could think of it kind of like a number line, right? Where this number line represents your x, you are getting closer and closer to some value of interest right here, and you're looking at what the y coordinate is doing. If the y coordinate were getting closer and closer to some number from both above and below, then you would say the limit exists. The limit is equal to whatever number y is approaching, right? And I mean, that's kind of straightforward, right? There's only a left and a right where x is concerned. There's only an above and below where y is concerned. So we could look at left hand limits, right hand limits, and if they're the same, then the overall limit exists. Easy peasy. However, when we move on to two and three variables, it is a little more interesting. So keep in mind, in the last video, we talked about how functions of two variables have two independent variables, x and y. So when we talk about the limit as x approaches a number, right, the two variable uh, analog of that would be an xy coordinate is approaching something. So rather than looking at, we've got our x-axis, our y-axis, our z-axis. So rather than just looking at one variable from the left and from the right, we actually have to look at xy coordinates. The thing is, if I'm approaching this coordinate, xy, we'll call it x naught, y naught, right? I can approach that coordinate from infinitely many directions. I can come from this way, I can come from this way, from this way, from this way, from this way, from that way, that way, that way, that way. Basically, instead of looking at just an interval, right, like along a number line, we're actually looking at a circle because you can approach this XY coordinate from any direction in this circle. So when we talk about neighborhoods with X, that's just like on this number line from here to here is a neighborhood. When we are looking at functions of two variables, our neighborhoods are circles, right? Every point in this circle is in the neighborhood of X naught, Y naught. And as we approach this point from any of these directions, we want to look at what the Z coordinate is doing. So for example, if I have a line or some kind of space curve there, and let's say that this point is directly above X naught, Y naught, right? Then this limit would exist and be equal to whatever the Z coordinate is, right? Which would also be the same if this were, say, a plane or like one of those tacos we talked about, right? So the thing about that though is that if there's any direction on that three-dimensional surface where the Z coordinate approaches something different than whatever that Z coordinate is, the limit does not exist. The limit does not exist. Right, but that's the idea. That's how we extend into two dimensions. When we go into three dimensions, it actually gets even more interesting. because rather than having a neighborhood that is a circle, functions of three variables have neighborhoods that are spheres. So as you approach a three-dimensional coordinate, right, so x, y, z, from anywhere within a sphere, which is a whole different infinity, right? A whole different infinitely many points, right? You would look at the behavior of the w coordinate, right? So one thing that you probably remember from practice, from actually taking limits in Cal 1, is kind of your general approach. In Cal 1, you were taught that your first step, your first thing you try is plugging in whatever x is approaching for x. If you get something with no issues, then that's your limit and you're done. Same thing applies for two variables and for three variables. The first thing you want to do is try plugging in the x and the y that you're given, that x and y are approaching. And if you get something with no hassle, no problem, then you're done. So with this one, if I plug in 1 for x and I plug in 2 for y, I end up getting 5 times 1 squared times 2 divided by 1 squared plus 2 squared. Notice I didn't write limit because I plugged the numbers in. And since this gives me something that actually has a value, I don't need to write limit. If I were simplifying, which is another thing we do, then I would need to continue writing limit because this is not the same as 5x squared y over x squared plus y squared. It might be at certain points, but it's not the same at every single point imaginable, right? So with that said, pay attention to your notation. So anyway, when I go to evaluate this, numerator I get 10, denominator I get 5. So overall, the limit is equal to 2. Easy peasy. And that should be the first thing you try. If I plug in the numbers, do I get something that is not problematic? The answer to that's yes, then you're done. If the answer to that is no, then the first thing I suggest is do more algebra, which is what I say in Cal 1 and Cal 2 classes also. But do more algebra, see if there's anything that you can do to simplify, and then from there, you might have more that you need to look at, which we'll also talk about. So let's look at another example. This is in the note page. I just ran out of paper. It's too late to go buy some right now. But yeah, so first thing, try plugging in 1 for x and 1 for y. If you do that, you'll end up getting 0 in the numerator, which could be okay. But then you get 0 in the denominator, and 0 over 0 is not a thing. That's an indeterminate form. And you might be thinking, can't we just L'Hopital it? No. No, this has more than one variable, and taking derivatives of something like that is a very different process that is a very big part of the later sections in this chapter, right? So you can't use L'Hopital. We don't really have an equivalent for that. So you have to do more algebra. One thing I can see here is that this looks like something I could factor. So one trick I like to use is look at your coefficients for both of these squared terms. If there's not a squared term, this would be like a constant term, right? If you multiply these together, you get -2. And if you add, or so basically you want to pick two magic numbers, we'll call them, that multiply to -2. Those magical numbers must also add to -1. So we need to think, are there two numbers that multiply to -2 and add to -1? There is, right? If I multiply 1 times -2, I get -2. If I add 1 plus -2, I get -1. So we can use those magic numbers to rewrite our middle term. So we get 2x squared, and I'm going to rewrite negative xy as plus 1xy minus 2xy. You see, if I were to combine those like terms, I would end up with that, right? So they're equivalent. And oh, that should be a minus. Okay. So after I split my middle term, I look at the first two terms, I look at the last two terms. What would be a greatest common factor in the first two terms? You'd get x. Both terms have a factor of x. So if I factor out x, what would I have to multiply that to get the originals? I'd have to multiply by 2x. I'd have to multiply by y. Now look at the last two terms. I notice that both terms are negative, so I can factor a negative out. And both terms have a factor of y, so I can factor y out. Then when I do that, what would I have to multiply minus y by to get these? 2x plus y. Notice this worked out to be the same thing. That means we're on the right track. So now both of these, so this expression now has two terms, both of which have a factor of 2x plus y. So we can factor 2x plus y, and we're left with x minus y. So I can rewrite the numerator as that factored form. And if I look at my denominator, this is the difference of two squares. So I know that this factors to x plus y, x minus y. So I did this work on the side. Now I can rewrite my limit as the limit as xy approaches 1, 1 of 2x plus y times x minus y divided by x plus y, x minus y. Now, if you notice, the top and the bottom have a factor in common. They both have x minus y. So those factors can divide, leave behind a 1 that we don't have to write. And now we're just taking the limit of this. So we're basically just doing limit of xy approaching 1, 1 of 2x plus y over x plus y. Okay, now if we go back to our original thing to try, we can plug in 1 for x and 1 for y. So I get 2 plus 1, 3 in the numerator, and 1 plus 1, 2 in the denominator, which means that my limit is 3 halves. So remember, when you get indeterminate forms like 0 over 0 or infinity over infinity, positive or negative, or some of the fancy ones from Cal 2, like 0 times infinity, or 1 to the infinity, or 0 to the 0, which is not 1. All right, you have different ways of dealing with that. It's not really anything you're going to have to worry too much about here, but 0 over 0, do more algebra. So there's a try it here for you to, you guessed it, try it. Pause the video, take a minute, do the things. And now that you've unpaused the video, um, let's try the first thing I said. Plug in the x, plug in the y. If I plug in 2 for x and 1 for y, I get 4 minus 4 is 0 on the top, and 4 minus 4 is 0 on the bottom. So it's not an easy one. I have to do some algebra. Luckily, this is some relatively easy algebra, because if you look in the top part, you notice that both of the terms have a factor of x. So I can rewrite my limit. Oops. Okay. And then in the denominator, this is also a difference of squares, right? This is x squared minus 2y squared, right? So we can write that, we can factor that as x plus 2y times x minus 2y. Then you have common factor in the numerator and the denominator. So you're really just doing the limit as xy approaches to 1 of x over x plus 2y. Now, if you go back and plug the numbers in, get 2 over 2 plus 2, so 2 over 4. So the limit is 1/2. Okay, now moving on to stuff that's more involved. Well, not really. Kind of. You'll see. All right. So here's the thing. In this one, I've already told you that the limit does not exist. Cue Lindsay Lohan. All right, but if you were to be just given this limit and told to evaluate this limit if it exists, you would start by plugging in 0, 0. That would end up giving you 0 over 0. So you'd say, oh, that looks like something I can factor. You'd factor x plus y times x minus y, but then you wouldn't be able to go anywhere further from that, right? Because you can't factor the denominator. And even though this is squared, there's not a way for you to rewrite the numerator that would help. So when you're caught in a situation like this where So when you're caught in a situation like this where plugging the numbers in doesn't work, trying to do algebra doesn't work, you might consider that the limit might not exist. It still might, right? And there are ways to do that, usually that involve the squeeze theorem, another relic from Cal 1. Um, but a quick and easy way for you to test if a limit ex or doesn't exist is to consider different pathways that you might approach that coordinate. So one example, I could approach along the x-axis. So think about it, we're approaching the origin, right? From within this circle. I could approach this point along the x-axis from either direction. Right, which means that essentially I would be looking at coordinates where the y is always equal to 0, right? Because every point on the x coordinate has a y, or on the x-axis has a y coordinate of 0. So essentially I could look at the limit as xy approaches 0, 0 of this function, but with 0 in place of all the y's. And if I were to do that, I would notice that this becomes x squared over x squared, which is also known as 1. Squared would be 1. Caveat. If you find that this equals something else, this does not actually mean that the limit is equal to that number. Because you have to consider that that you can approach this point from literally anywhere on that circle. So if you only test two things and they happen to be equal, that doesn't actually tell you anything. There's not a way for you to test infinitely many points. So if you do this kind of a test two different ways and get the same number, that does not imply that the limit exists. That just hasn't shown that it doesn't exist, right? For you to show that the limit does exist, you'd have to use other things, right? Like Moore algebra or squeeze theorem or all sorts of other possibilities that we really aren't going to touch too much on. Um, so anyway, x-axis is one way that we could do it. Similar way, we could also look at the y-axis. This would be like if I were approaching the point from above and below on the y-axis. And if that were the case, we'd look at the limit as xy approaches 0, 0 of basically this function, but now the x's are going to be 0. Because remember, every point on the y-axis has an x coordinate of 0. Okay. And if I were to actually compute that, this would become -1. When I square -1, I get 1. Those do agree, but again, that does not mean anything. We've only shown two possible pathways. There are infinitely many. And in this example, I'll show you another one that's fairly common, approaching along the line y equals x. So this would be like if we were at this 45-degree angle and we were coming in towards that point from both directions. So with this one, I want you to remember that every point on that line, y equals x, will have x and y coordinates that are the same. So I could replace the y's with x. I could replace the x's with y. It doesn't matter, right? But when I'm testing along this line, I'm just replacing one of the variables with the other. So I end up getting 0 in the numerator. I end up getting not 0 in the denominator, right? That's 2x squared. And when I square that, I'd still have 0 in the numerator and not 0 in the denominator. That means that this limit would be equal to 0, which is exactly what we needed. See, the way that we show that the limit does not exist is by showing that we get different values if we approach from different directions. So because this does not line up with the other limits that we got, that tells me that the limit does not exist. So with that said, let's look at a couple more examples to kind of get a little bit of fluency in it's so sharp. Get a little bit of fluency in kind of approaching these problems. So next example, let's say we want to evaluate this limit. First thing you try, plug in the numbers. I get 0 over 0. Can't really do any algebra with that because I can't really factor that. I mean, I could do x plus y cubed, x minus y cubed, but that's not going to help because this is x times y cubed. If this were a plus or a minus, then I'd be fine, right? But because it isn't, I can't really do any algebra. So I might be thinking, okay, this probably might not exist. I need to prove it though. So I'm going to start off with my tried and true x-axis, y-axis. So for the x-axis, y's are equal to 0. We would look at the limit as xy approaches 0, 0 of x squared minus 0 to the 6 over x times 0 cubed. Oh no, I have a 0 in the denominator. Oof, can't do that. here's another thing. If I were to try y-axis, I'd have the same issue. Right? I'd have 0 in the denominator, and we can't really do anything with that. So we are going to look at y equals x, right? Because logically that would be the next thing that I try. But I want to kind of point something out here. We're going to have to come up with a different way aside from x-axis, y-axis, y equals x, because we need to have something to compare y equals x to. So one thing that we could consider is plugging in something that will zero out our numerator, but not our denominator, right? And I know that that's possible just by looking at my numerator, right? If I plug in the right thing for x, I can get y to the sixth. So if I let x be equal to y to the third, that'll accomplish my goal. So the limit as xy approaches the origin of y cubed squared minus y to the sixth over y cubed times y cubed. Right, if I look at my denominator, this will become y to the sixth. In my numerator, we end up with y to the sixth minus y to the sixth. Guess what that is? That's 0. So I have 0 over not 0, which is equal to 0. So you see, by choosing the right thing to plug in for x or for y, I can basically make a limit that's easy for me to evaluate. And when you're going through and doing these problems where you have to show that a limit doesn't exist, or you suspect it might not exist, so you're trying to prove it, this is a strategy. Now, the other one that we mentioned was y equals x. So for that one, I can replace the x or the y. Again, it doesn't matter. So I'll replace the x this time. All right, so we'd end up getting y squared minus y to the sixth divided by y times y cubed. So this would basically be limit as xy goes to 0, 0. And then I notice in the numerator, I can actually, well, I could factor out a y squared. So that'll leave behind 1 minus y to the 4. In my denominator, this becomes y to the 4. So what's going to happen is this will simplify to 1 over y squared. And because I'm subtracting in the numerator and I only have one thing in the denominator, I can split this into two terms, which is going to be something that actually makes this doable. So don't drop the limit. We have not evaluated yet. Parentheses because there's more than one term now. Right, so 1 over y squared minus y to the 4 over y squared, which is going to be y to the 2. So now that I look at this one, let's think a little bit. As y approaches 0, this term will approach 0. But as y approaches 0, this term will get really, 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 really big, right? Because if I divide by a small, 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 small number, I get a big, 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 big quotient, right? So this becomes a very large number. As y approaches 0, this approaches infinity. This approaches 0, and I'm subtracting it from really, really big number, which means that this would be an infinite limit, which is not the same thing that I got for the other limit I did. right? Not the same thing. Because these are different, that means that the limit does not exist. Yeah. And believe that was actually our last example. Oh, wait, it's not. Silly me. All right, that was the last limit example. Now I'm going to talk about continuity. So in Cal 1, you learned that if the limit is equal to the y coordinate at a point, then your function is continuous at that point. Same thing applies to 2 and 3 variables. If the limit that we get is equal to the z coordinate for 2 variables or the w coordinate for 3 variables at the actual point when we actually evaluate, then our function is continuous at that point. The thing is, we typically, as you've seen throughout Cal 1 and Cal 2, are more concerned about continuity on an interval. And this all kind of goes back to what we did with domain, right? Because a lot of functions are continuous on their domains, right? So for questions like this, where we want to discuss the continuity or figure out whether a function is continuous on an interval, we need to do what we do to find domain, look for math no-nos. If we don't have a specific interval we're looking at and it just says to discuss, right, then we look for the domain. And otherwise, we only need to look at the values that are on the interval that we're given. So first function, look for math no-nos. Denominator cannot be 0. So x squared plus y squared cannot be 0. Well, remember we said that squared number, or if you square something, you always get a positive. If I add two positives together, it's not possible to get a negative, right? Yeah. So there would never be a case where y squared would be the negative of x squared, which means this would only happen, right? X squared plus y squared would only be equal to 0 if x and y were equal to 0. So basically, the x, y coordinate cannot be 0. Um, there aren't any other math no-nos, right? So I don't need to worry about anything else. There are no positive, or there are no even roots, there are no logarithms, there are no trig functions that have limitations like tangent or secant or any of their cos. Yeah. So that's it for that one. We know that f of xy will be continuous for all, and I'm going to write this symbol, it means for all. It's math symbol language. Coordinates xy that are not 0, 0. So basically, this function is continuous everywhere except the origin. Now, for the second one, again, we still have this math no-no that the denominator cannot be 0. Right? If I rearrange this equation, I get that y cannot be equal to x squared. So essentially, we know that g of xy is continuous for all ordered pairs x, y that are not equal to x comma x squared. In other words, we know what the graph for y equals x squared looks like. It's a parabola, vertex is at the origin, and it opens up with a equals 1, right? Essentially, yeah, essentially if I were at any point on that parabola, my z coordinate would be either positive and or would basically be approaching an asymptote. Right? But instead of an asymptote being just a line, it's a surface, right? So we did this in one variable functions. Basically, we would have, so that's y and that's x, that's z. Basically, we would have an asymptote along this parabola. So that's y equals x squared in the xy plane. Essentially, this entire taco is an asymptote, asymptoco. All right. Now let's look at the continuity of a three variable function. All right, so four-dimensional graph. So for this one, again, we still have the same, yeah, we still have the same math nona that we're looking at. Denominator cannot be zero. So basically x squared plus y squared minus z cannot be equal to zero. If I rearrange this, I end up getting that z cannot equal x squared plus y squared. So the graph for this is actually a three-dimensional surface that looks like basically a parabola if you spun it around and around. I think it kind of looks like a beanie. Should wear a beanie today. Missed opportunity. Yeah. So in this case, the asymptote is a three-dimensional surface. So if I were to plug in any coordinate on this paraboloid, my W coordinate would be infinite. Really, it would be approaching an asymptote, but this time the asymptote is a three-dimensional surface. Actually, it's a hypersurface. Yeah. Can't really visualize that one. But anyway, that's how you look at continuity. For your information, though, I will kind of give you an idea of what looking for other math nonos could look like. So let's say, for example, I have something like that, right? Remember, with logarithms, you can't take log of zero, you cannot take log of a negative. So basically, the inside of the log would have to be greater than, not equal to, just greater than zero. That's how you'd handle a logarithm. If I had a trig function, we know sine and cosine are continuous everywhere, so if I had sine of x squared plus y squared, there would be no limitation. I could take sine of any angle and that's fine. But if I had something like tangent, and let's do a three-dimensional for funsies, right? If I have something like this, the math no-no would be that I can't take tangent of pi over 2 or any odd multiple of pi over 2. So essentially, the inside of the tangent could not be equal to pi over 2 times any odd number. And 2n plus 1 is how you write odd number for any integer n. If I want to say any integer n, I would say for all n in the integers. All right, but basically that would mean that you couldn't be on a sphere with varying radii, right? So those are really the only other kind of math no-nos that we haven't looked at. Like if you get a fourth root or a sixth root, then you treat it the same way you would a square root, right? And if you're in the denominator, you can't be zero. Right? So that's just an overview of the different kinds of no-nos that you could potentially encounter, whether here or in the wild. And with that, I bid you good night and happy mathing.